Okay, it's Brian, and we're talking about our review and practice from day 2. And this was the material from chapters 5 through 8 in the text. So that was like forces, circular motion, and then torques. And we've got 4 scenarios to look at. Something I want to point out to folks, or remind folks of, is that the way that we're presenting these problems is exactly the way that will be presented on the final exam. You're going to have a scenario, you're going to have some information. Okay, and then based on that, you're going to have 2 multiple choice questions and then a problem. Now for this first scenario, this sliding on the ice scenario, I want to give you a pro tip. There's no reason why you have to answer the questions first. People do because they come first, but there's no reason you have to do them that way. And actually in this case, it's much, much better if you do them after we solve the problem. So what I'm going to do is I'm going to take a look at the scenario, I'm going to solve the problem, and then I'm going to come back and look at the questions. And I strongly advise you to pay attention to the order that you do things, and if the questions aren't making sense and you find yourself spending lots of time on them, come back to them. After you've done the problem, it might make a lot more sense. So the basic detail in this scenario is that there's a 20-kilogram stone and it's given a push across the ice and it moves 40 meters before it comes to rest. Okay, that's the crucial piece of the puzzle. Now, we're told here, let's see, the curler pushes the stone to a speed of 3 meters per second over a time of 2 seconds. Questions, if the stone slides 40 meters before coming to rest, what is the coefficient of friction between the stone and the ice? And then what force did the curler apply to get the stone up to speed? Here's my strategy. This problem is one that we can clearly break into 2 parts. Okay, there's the push. Oh, let me put that in black. That's going to be more stylish. There's the push. Then there's the slide. So during the push, okay, the stone is starting at rest, and then it speeds up. And it goes from a speed of 0 meters per second to a final speed of 3 meters per second. And it does that over a time of 2 seconds. Now for the slide, what happens is this. It starts at 3 meters per second, and then it slows down. And it slows down over a long distance. It travels 40 meters, but it starts at a speed of 3 meters per second, and it finishes at a speed of 0 meters per second. And we don't know the time for that. But these are 2 distinct phases of the motion, and you want to be clear that you've got those 2 phases. And we're going to treat them in turn, but first I want to treat the slide. I want to do the slide, and then I'm going to come back and treat the push later. Now we've drawn motion diagrams, but of course the other thing which we need to draw is free body diagrams. And when I was talking to people about solving this problem, I reiterated that remember, any time you solve a problem that has anything to do with forces, you've got to draw a free body diagram. And folks were hesitant to do it, but don't be. This just helps you wrap your mind around the problem. So I got my motion diagram. Let's take a look at the slide. Here's my stone. What are the forces that act on it? Well, there's a weight force which acts downward. There's a normal force which acts upward. And there's a kinetic friction force which is opposite the motion. Okay? Oh, heavens to Betsy. Then I can say some things based on this. There's no vertical motion, so I can say the normal force is equal to the weight force. That's just equal to m times g. And then I can say the net force is just equal to the force of kinetic friction, because that's all that's left. Well, and I can also say kinetic friction is equal to mu k times the normal force. Oh, but I know what the normal force is equal to the weight force, so it's just equal to mu k times m times g. Oh, heavens to Betsy, you know what else I can say? F net is equal to ma. So putting it all together, I can say m times a is equal to mu k times m times g. Now check out what happens next. The mass goes away, and I just have the acceleration. And the acceleration is equal to mu k times g. Oh, you know what else I can say about the acceleration? The stone slides for 40 meters before it comes to rest. So looking at the motion, I can say, use my basic relationship for motion with constant acceleration. And remember, we had a few, and I don't know time, so I'm going to pick the one that doesn't involve time, which is this one right here. And I can say, look, I know the initial velocity of the stone, that's 3 meters per second. I know the final velocity, that's 0. I know the distance that it travels, that's 40. I can solve for what the acceleration is. And the magnitude of the acceleration that we get is about 0.1125 meters per second squared. That's what I'm going to get here. And that makes sense. It's a very small acceleration. It slides for a long, long, long way. And with that number in hand, I can take that number and I can put it in here, and I can solve for what mu k is. And if I do that, I get a value of mu k of about 0.015. Okay, and I'm going to say that makes sense because ice is slippery. Now, next piece, I have to come back and take a look at the push. Well, for the push, okay, I've got a normal force pushing upward, got a weight force pushing downward. Those, as usual, are equal to each other. And I've got a force of the push. That's what we're looking for. And I've got a friction force opposite the push. And since it's sliding, it's going to be kinetic friction. F net is equal to F push, the force in the direction of the motion, minus Fk. Right? Oh, and I can compute Fk because I have all the numbers I need for it over here. We calculate that for the slide. And I can also compute F net because F net is just equal to m times a. And I know what the acceleration is in this case. In the case of the push, it goes from 0 to 3 meters per second in a time of 2 seconds. I can just compute the acceleration using my basic definition. It's just equal to delta v over delta t. So I compute the acceleration. I put the acceleration in here. I can compute Fk, and I can solve for F push. And if I do that, I get a force of 33 newtons, which isn't that much force. And that makes sense because this is kind of a gentle sport. And now, with all that done, I'm going to go back and take a look at my questions. And let's take a look at question 2 first. So question 2 asks this: suppose the sun's mass is increased to 40 kilograms. Oh, but check it out. For the slide, when we solved this problem, the mass canceled. So the mass doesn't change anything about the motion. So it won't travel a longer distance. It won't travel a shorter distance. It'll travel the same distance. But what is true is the force of friction will be greater because the force of friction is equal to mu k times the normal force, which is equal to mu k times the weight force. The weight goes up, normal force goes up. The coefficient of friction is just all about stone and ice, and that's not going to change. That's one of the things about coefficients of friction. So see how much easier it was to answer question 2 after having done the problem. Now, if, coming back to question 1, okay, if we want to adjust the trajectory of the stone, we make it go 3 meters farther. Well, thinking about what we did here when we solved for the slide, if it goes 3 meters farther, what I do is I decrease the coefficient of friction. If I decrease that, I'm going to have a smaller acceleration. It's going to go a greater distance. And so that one is going to be A, and the second one is going to be D. And it was much easier to do those after I've done the second piece. And you should feel comfortable doing that. Solve them in any order you want. Don't let the man tell you what to do. All right, let's move on to the next problem. And the next problem has to do with a falcon, okay? And so a falcon is pulling out of a dive, and we're given kind of a picture of a falcon pulling out of a dive, okay? And what they do, basically, is the falcons kind of like go in these deep, deep, deep dives, and then they're going really, really fast, and they're hurtling towards the earth, and so they got to redirect. So the path of the falcon is it comes down, and then it says, whoops, I want to turn the corner and not slam into the ground, so it turns a corner. Now, let's take a look at this whole problem and strategize. And what I'm going to say is, we seem to be focusing on the circular motion of this arc here. So this is a circular motion problem. We want to think about it in those terms. And in this case, I'm going to answer the questions first. And the questions ask, in this picture, at the bottom of the arc, what is the direction of the net force on the falcon? Well, we know the acceleration in circular motion is directed towards the center of the circle, and so clearly the net force must be directed towards the center of the circle as well. And so the correct answer for that one is going to be just up in terms of the picture that I've drawn. And then it asks about apparent weight. Now remember, apparent weight is the magnitude of contact forces supporting you. And for these purposes, lift is a contact force. The air is pushing on the falcon, it is touching the falcon. And at this instant, when it's at the bottom of the arc, the forces acting on it are a downward weight force, an upward lift force, And we know the lift force has got to be bigger than the weight force because the net force is directed upward. So since that's true, we can say lift is greater than W. The lift is going to be the contact force supporting the Falcon. That's going to be its apparent weight. So the apparent weight is greater than the actual weight. And so the answer to this one is A. Now, next problem, we're going to look at the problem. And the problem starts out with a Falcon who does a free fall from a height of 30 meters. Okay, so it falls 30 meters. And then it pulls out by flying in a circular arc of radius 50 meters. Okay? And then we're looking for the magnitude of the lift force at the bottom of the arc. So when the Falcon gets right here, okay, what is the magnitude of the lift force? Now, in this case, we did the questions first. I'm going to translate what I said about the questions. I'm going to put it down here. There's an upward lift force. There's a downward weight force. And the net force is going to be equal to the lift force minus W, because F net is directed towards the center of the circle. Okay, we know that that's true. And I can also say, since it's circular motion, the acceleration is equal to V squared divided by R. Oh, well, F net is also equal to M times A. So if I know the acceleration, I can take it and I can substitute it in here, which means I can compute the net force. And I can compute the weight force because the weight force is just M times G. Oh, and with that in hand, then I can compute the lift force. So what I need to do is I have to find out the velocity of the Falcon. Well, I can figure out the velocity of the Falcon because this segment of the motion when it's starting is just free fall, and the acceleration is negative 9.8 meters per second squared. It starts at a speed of 0 meters per second. It finishes at a speed of I don't know. That's what we're looking for. And remember, we have this basic relationship for motion with constant acceleration, of which free fall is a type, that says Vf squared is equal to Vi squared plus 2 times A times delta y. Now delta y, the change in vertical position, is equal to negative 30 because it finishes 30 meters below where it started. The acceleration is negative 9.8 meters per second squared. Vi is equal to 0, and so I can figure out what Vf is. And if we do that, we got a final speed of 24 meters per second. Okay, we can use that going forward. And the 24 meters per second I can take and I can put in here. And with that in hand, I can calculate the acceleration. With that in hand, I can calculate the net force. And with that in hand, I can calculate the lift. And I will leave that algebra to you. But if we do that, what we end up with is that the lift force is 17 newtons. And that's a bit more than twice the weight. And that sounds reasonable because Falcons are kind of extreme flyers. And we expect this to be something kind of like amazing. And that number, in fact, is. And by the way, these are realistic numbers from for a Falcon. I got numbers from a research paper, kind of like describing their motion. There we go. So there's the Falcon. Next, we're going to look at cheetahs, and cheetahs turning a corner. It's like turning a corner. I'm immediately saying to myself, oh, heavens to Betsy, this sounds circular motion-y. And in one study, the maximum acceleration when rounding a corner was 18 meters per second squared, which is kind of crazy. Okay? And then we got a couple of questions about cheetahs rounding corners. Then we have a problem about cheetahs rounding corners. Okay? I'm going to go ahead and do the questions first. And if I get stuck, I will change tack and I will do the problem first. So a cheetah is achieving a centripetal acceleration while executing a turn at 14 meters per second. Well, if it's going around a turn, and the acceleration is directed towards the center of the turn, and the acceleration is equal to V squared divided by R, oh heavens to Betsy, we know what the acceleration is. We're told that. We're also told what the cheetah's speed is. So it's a really simple matter to calculate the cheetah's speed. And if we do that, calculate the radius of the turn. And if we calculate the radius of the turn, I get that it's 11 meters. And of course, to the nearest number we have in here is 10 meters. That's my approximate radius of the turn. Next up, suppose the cheetah was running east at 10 meters per second and began a turn of radius 10 meters. How much time would it take for the cheetah to completely reverse direction? Well, we're treating this as a circular motion problem, okay, because it turns corners in circular arcs. Cheetah's going east and turns around and ends up going the other way. And if you think about this, that's just 1/2 of a circle. So it's going to be 1/2 of the period for circular motion. And for circular motion, we said that the speed was equal to 2 pi r over t. So the period was equal to 2 pi r over v. And so 1/2 the period is just equal to pi times r over v. Oh, well, I'm told the radius of the circle is 10 meters, and the speed is 10 meters per second. So this is 10, this is 10, and so I just end up with 1/2 the period is equal to pi, so it's equal to 3.14 seconds to the nearest second, so that we can match numbers in the table. It's just 3 seconds. And the crux of the biscuit, the important piece, was to recognize that what the cheetah did was it basically did 1/2 of a circle. That's the sort of thing we want you to be thinking about. Now, the next piece of the puzzle is we're going to be looking at the turn. And it says here, when an animal executes a turn, they lean so the total ground force is along their body. Okay. Now, remember what we said about this. Okay. So we said, so here's the ground, and suppose I got a cheetah on the ground, and the cheetah is executing a turn. So the cheetah's like in a turn like here, and I'm not very good at drawing, so this is my back view of my cheetah. The force from the ground is going to be along the cheetah's body, okay? But the ground force is a sum of two forces, and there's two different kinds of forces the ground can exert on you. One is a normal force, and the other is a friction force. Okay, and it's going to be static because the cheetah is not sliding. So the sum of the normal force plus the friction force is equal to the ground force. I'm going to redraw that as a triangle this way. Oh, by the way, too, I'm going to go ahead and put in the lean angle. That's what we're looking for ultimately. So I have a lean angle there. If I redraw my triangle, I've got the static friction force, I got the normal force, and then I sum those two, and I end up with the ground force. Oh, heavens to Betsy, I got a triangle here with an angle theta. I'm going to go ahead and write down some trig relationships. I can say the tangent of theta is equal to n over fs. And I can also say the ground force is just equal to the square root of the sum of the two sides. It's a Pythagorean theorem thing, so it's the normal force squared plus the friction force squared. Square root of that. Okay, so that's good. Oh my goodness. And the apparent weight, of course, which is what we're looking for here. The apparent weight is just the contact forces supporting you. In that case, this is the ground force. So that's what I'm looking for. And I'm looking for the angle that cheetah leans at. Oh, heavens to Betsy, I've got this. So what I need to do to complete my problem is I've got to figure out what the normal force is, and I've got to figure out what the friction force is. Now, let's do a free body diagram for the cheetah. There's a weight force acting downward, there's a normal force acting upward, and there's a friction force acting towards the center of the turn. Well, the net force is just equal to Fs, okay? And the normal force is equal to the weight force. Oh, but the net force is also equal to m times a, and the acceleration, since it's circular motion, is v squared over r. Oh, heavens to Betsy. Oh, actually, I didn't have to do that. Let me take that away. I'm told what the acceleration is. The acceleration is 18 meters per second squared. The mass of the cheetah is 50 kilograms. Oh, heavens. That lets me figure out the normal force. And, I'm sorry, figure out the friction force, which is the net force. The normal force is just equal to the weight force, but that's just equal to m times g, and I know m, that's 50 kilograms, and I know g, that's 9.8 meters per second squared. So that lets me calculate what n is. I can also calculate what fs is, and if I know n and fs, I can calculate the tangent of theta and the ground force, and if I do that, what I get is I get theta is 29 degrees, and I get that the ground force is 1,000 newtons, and that's about twice the cheetah's. That's about twice the cheetah's weight. And that sounds like a very extreme term, but cheetahs are extreme athletes. And so my net result is very reasonable in terms of my understanding about how the world works. Last problem we want to look at. Last problem that we're going to look at is triceps torque. Okay, and this looks like one of those static equilibrium problems which we looked at back in chapter 8. Okay, that's what this looks like. Okay, and so the question is asking about your triceps. And if you didn't do this when you were solving this problem, you should get that physical reference. Go ahead and take your hand, put it out, push down on the table, and feel that force that your hand is doing. And then reach back and feel your triceps and feel it pulling up. And we got a couple of questions and we got a problem. I'm going to go ahead and do the questions first. So let's see, pushing down on the table. Okay, and so if you're pushing down on the table is pushing upward on your hand. We know that that's true, and that's going to be a normal force, okay, of the table on your hand. And then I'm going to treat in this problem the object of interest is your lower arm. That's going to be my object of interest. Okay, so check it out. The triceps is pulling up on your lower arm. The table is pushing up on your lower arm. There must be a force from the bones in the upper arm on the lower arm, and it has to be directed downward. Okay, I'm going to call that F sub J. That's the force in the joint. That's typically what we called it, and that has to be directed downward. So the table pushes upward on your hand, and the upper arm pushes downward on the bones in your lower arm. And then the question asks here, if you're doing this, what force must the triceps muscle provide? Well, what I'm going to do first is draw a simplified view of the situation. There's the upper arm. Here's the lower arm. Here's the joint. The table is pushing upward, and we're pushing upward with a 90 Newton force. And the question asks, what is the muscle force? I'm just going to call this F sub T. That's the force of the triceps. What is the force that the triceps is pulling up with? And then there's also going to be a force in the joint, which is going to be going downward here to make my forces balance. Oh my goodness. And the arm's not going anywhere. So this looks like a situation where the sum of the torques is equal to 0 and the sum of the forces is equal to 0. But I only really need to do the torques. And I'm going to say this. The triceps torque is rotating the arm this way. The force from the table is rotating the arm this way. And so I'm going to say the torque of the triceps is equal to the torque of the table, which I'm going to write out. I got two T's, shame on me. So those two torques are going to be equal. And the magnitude of the force of the torque due to the triceps is equal to the force of the triceps times this distance. And that distance is 2.4 centimeters. So it's going to be F sub T times 2.4 centimeters. Pro tip, I didn't change it to meters, and we'll see why that works. That's going to be equal to the torque due to the table. The torque due to the table is the force of the table times the distance, and the distance is 30 centimeters. So it's equal to the 90 newtons times my 30 centimeters. And then I'm trying to solve for the force of the triceps. Oh heavens, I can do that. I can do that. Because on this other side, I got 90 newtons times 30 centimeters. Now notice this. I'm going to take that 30 centimeters. I'm going to divide it by 2.4 centimeters. Since they're in the same units, everything balances. Everything balances. And so I can just not worry about converting the units. As long as the units are the same, everything's good. And if I do this calculation, what I get is the force of the triceps is equal to 1,100 newtons. That's bigger by like more than a factor of 12 than the force that the table exerts. And that's reasonable because we know that your muscle forces are significantly larger than the forces that your body exerts externally. That's one of the things we learned when we were doing that part of the course. And so we end up with an answer which makes sense in terms of our understanding about how the world works. And I'll be back on Friday with 4 more problems to get you ready for taking a test. Thanks much.